Okay, let me go ahead and go over this first one here. So we want to find the 6 trigonometric functions for 2 pi over 3. Okay, now what we need to do first of all is figure out, well, which quadrant is this in? 2 pi over 3. Well, remember, 2 pi over 3, that's 2/3 pi. So it's 2/3 way around a half circle. And remember the ordered pairs that are associated with the 3 on the bottom, on the unit circle. The ordered pair, the ordered pairs, or the ordered pair that's associated with that, with the 3 on the bottom, is going to have 1/2 on the x and square root of 3 over 2 on the y. Now we're in quadrant 2, so the x coordinate's negative. So what we do is immediately recognize, okay, what ordered pair is associated with that? Remember, we have 3, 4, and 6 as denominators. And of course 2, but once we get what ordered pair is associated, we think about which quadrant it's in, we calculate that, and then I know this. I know that sine of alpha is equal to the y coordinate. Cosine of alpha is equal to the x coordinate. Okay. Now, we have the reciprocals, right? So I might as well go ahead and say, well, cosecant alpha is the flip of sine alpha. And secant alpha is the flip of cosine. So if we get sine and cosine, immediately we can get the reciprocals. And further, if we look at tangent, tangent is just sine over cosine, or in other words, y over x. So this is going to be negative square root of 3. See? Square root of 3 over 2 divided by negative 1/2, that reduces to just the negative square root of 3. Then cotangent is the flip of that. Okay, now for 7 pi over 6, we think about the ordered pair associated with that, and that's going to be 1/2, well, square root of 3 over 2, 1/2, right? Now, I've got to determine if are the coordinates positive or negative. Well, 7 pi over 6, I need to know where is that? Which quadrant is that in? 6 pi over 6 is pi. So 7 pi over 6 is 1/2 turn and then 1/6 of the way around another. So that would put it in quadrant 3. And in quadrant 3, everything is negative. Well, the sine and the x and the y are negative, okay, both of them. So then it's just a matter of remembering sine is the y, cosine is the x, and then we've got the reciprocals. And this is going to be 1 over the... No, I'm sorry. What am I doing? Getting ahead of myself. It's the flip of sine. And secant is the flip of cosine. Flip. That's the mathematical term, right? Flip of it. The reciprocal, maybe. So we've got sine, cosine, cosecant, secant. And then we've got tangent, which is the y over the x. So this is going to be 1 over the square root of 3. They're both negative, so it makes it a positive. Now cotangent is going to be the square root of 3, just the flip of tangent. Okay, the negative pi over 4. Now we know pi over 4 is associated with square root of 2 over 2, square root of 2 over 2. Negative pi over 4, okay, so that's a clockwise rotation, just 1/4 of a halfway around the circle, and that's going to mean in that quadrant the y's are negative. Okay, so here we go. We've got sine is equal to negative square root of 2 over 2. cosine square root of 2 over 2. And then cosecant is, the reciprocal of it. So it's going to be negative 2 over the square root of 2. Secant, 2 over the square root of 2. And then we've got tangent, which is negative 1. Cotangent is negative 1. Remember, tangent is y over x, and then cotangent is just the reciprocal of that. Okay, now we've got a degree one over here, 480 degrees. So we think a little differently in determining where this is. We think in terms of, well, here's the way I think about this. I think, okay, one full revolution is 360 degrees. Well, I've passed that. But where am I? So what I do is I take 480 minus 360, and I get 120. So the angle, the ordered pair, I'm looking for the ordered pair associated with 120 degrees. Okay? Now, so you remember the unit circle, and you remember when you were making the unit circle, you've got, now remember you've got 60, whoops. Let's go back and think about how that is. I'm just acting like we don't remember anything about, the unit circle here, but we can go back and kind of calculate. So remember, here was 30, 60, 90. 90's right here. What's after 90? 120. There it is, right? So we're looking for this ordered pair right over here. And remember that one, now down here, this would correspond to the 30-degree angle down here. This is corresponding to the 60 over here. So this would be, the ordered pair would be like, what would it be? Negative 1/2 square root of 3 over 2. Is that it? Okay. Now, I don't know which method or how you go about thinking about this, but you need to be able to determine what quadrant it's in and what ordered pair is associated with it. And I tried to think out loud to kind of show you how I do it. Okay? So now we have, sine delta is equal to square root of 3 over 2. Cosine delta, negative 1/2, and then cosecant, the flip, and then secant, and then tangent. Tangent's going to be square root of 3 over 2 divided by negative 1/2, negative square root of 3, and then cotangent is the flip of that. Okay, so let's look at this first one here. Now, first thing you recognize is it's sine. And what we want to do is we want to figure out how low this thing goes, how high it goes, where does a period start and where does a period end? Just one. I mean, there's infinite starts and stops. It goes on forever. But we're just trying to get an idea, just a basic idea about this function. Now, normally sine oscillates about the x-axis, but not this one. It's been raised up 7 units. So this line of oscillation is 7. That's the vertical shift. Now, oh yeah, I forgot. Go ahead and put in the sketch. What we don't want to get bogged down in is trying to figure out, okay, about where is this on the x-axis? Let's just make a rectangle, put a typical period there, and we can expand it as we see fit. Okay? And this will, like if we want to see this graph with our calculator, this will help us to know how to set the windows as well. Now, from 7, we go up an amplitude So we go up 10 and we go down in amplitude. So immediately, vertically, we know this graph is oscillating between 4 and 10 forever. Now, if we want to see a start for a typical period here, normally the sine starts at 0. But we want to see, okay, where would it start at? Where is the point 0, the x equals 0, after all these transformations? In other words, divide it by b and add c. Okay? So what we get is 4. That point 0, 0 is now over here at 4, 7. Now let's see where it ends. Over here we've got 2 pi, divide it by 2 pi, divide it by b and add c. Well, that's going to be 5. So a 5 goes in there. So there, that helps us to see where a typical period starts, where it stops, what the low point is, and what the high point is. Now, if you wanted to know, well, where does this graph have its maximums? Well, normally, sine has a maximum at pi over 2. So you could take pi over 2 and divide by 2 pi and add 4, and you would find, okay, where this graph has a maximum. Now notice the period of this graph. The period of this function is 2 pi divided by 2 pi. We can always find the period by dividing by b, and we get 1. And notice the distance here, that's 1. 5 minus 4 is 1. Okay, let's look at this one. This one is negative sine. So we remember, okay, negative, that's going to flip the graph. It's going to turn it upside down. So let's do that sketch real quick. Okay, there's what sine looks like. It oscillates about 5. Okay, it goes up in amplitude, and it goes down in amplitude. The amplitude is 3. Right? So it's going to go up 3, it's going to go down 3. So it's going to oscillate between 2 and 8. Okay, so that's valuable information. Now let's see where it starts. 0 divided by pi plus 1, it's going to start here at 1. Now it normally would end in 2 pi, but we divide by b and add c, and we get 2 plus 1 is 3. So there we have that. Okay? And if you calculate the period 2 pi divided by b, 2 pi divided by pi, you get 2. And notice that is the length here, 2. Okay? From start to finish takes 2. Okay? Now let's look at this one. Okay? Once again, we've got negative 3. We add 5 to it, and we get 2, right? We subtract 5, and we get negative 8. Okay. Forgot to draw it. Use a different color. Okay, so it's sine. There we go. It's going to start. Oh, be careful. It says x plus 1. Okay, so c is like negative, right? So it's negative 1. Okay, it starts at negative 1. So here's what we got. It ends over here at 2 pi divided by 4 pi minus 1. So that's going to be 1/2 minus 1. So I guess that's negative 1/2, isn't it? Okay, so this gives us a kind of a start where to set our calculator if we want to explore this graph more. Okay, let's try this one. Cosine, okay, starts up here. Goes up. Man, I really dropped the ball on the cosine over there. Let me see if I can draw it better. I don't know. I'll probably not, but I felt bad about that drawing. You're thinking, hey, that's not much better. Okay, so here's 3. We go up 5 to 8. We go down 5 to -2. And we're going to start at 1. Okay. Now let's see where we end. 2 pi divided by pi over 3 plus 1. Okay, the pi's cancel. And this looks like it's 6 plus 1, which is 7. See, if you multiply the top and the bottom by 3, the 3's cancel, and up top you get 6 pi over 6, which is just 6. Okay? So this over here is 7. Okay, on this one, this is an upside down cosine. Okay, so we got to draw the upside down cosine. It has a vertical shift of 2. Now the amplitude is 1. So we add 1 and we get 3. We subtract 1 and we get 1. So 2 plus 1 is 3. 2 minus 1 is 1. It starts here at 3. And it goes to 2 pi divided by pi over 4 plus 3. Now, if you work this out, I think 2 pi divided by pi over 4, that's going to be 8, right? So there it goes, 11. Okay, let's think about, so let's suppose we want to model this with the cosine. Okay, so we want to model this with cosine. So what it amounts to is we've got to find A, B, C, and D. Now, D is the vertical shift, and remember, it's going to be the average midway between the low point and the high point. So it looks like that's going to be 2 plus 6 divided by 2. See, I just got that right off the graph, just looking at it. And that's going to be 4. 8 divided by 2 is 4. So here's what we've got. So we've got this thing. Okay, there's the line of oscillation. Now from there, you go up 2 to get to the max and down 2 to get to the min. So you could say, okay, A is going to be the max minus D, which is 2. And we can just eyeball it, though, and see. You know, we don't have to go through these calculations. We can just look. You know, if you get used to it, if you work at it enough, you start to see, I can see what the A, B are pretty easily. So we've got the vertical parts. Now, I need to figure out what B is. Now, because we're going from 0 to 2 pi, that was given to us. To find B, we just need to find out, well, how many complete cycles take place between 0 and 2 pi. And we can do that by counting these high points. There's 1, 2, 3, 4, 5, 6. So B equals 6. The only thing left is to figure out what C is. Well, C is going to be pretty easy because since we're using cosine, because normally cosine has a max at 0, but this one has a max at 0.811, so that must have been the shift. That must be the horizontal shift. So we've got A is 2 cosine, B is 6, x minus 0.811, Plus 4. Yeah, there we go, plus 4. Okay, so notice, looking at that graph, we took note of where the high point was, where the low point was, and we took note of what the period was, or how many cycles take place in a period, and then we took place of when the max occurs, or the x value where the max occurs. With that bit of information, we were able to write our model. Now, let's think about this one. So we've got this distant planet where there's a sea of methane. Okay. Now, the methane raises from 2 miles to 10 miles in depth. So it's like we have a high tide and a low tide, right? So what they gave us here was the low point and the high point. We're not looking at a graph now, we're looking at the wording. So we've got a max of 10. We've got a min of 2. Now, the 2 mile depth occurs at 2 a.m. And the 10 mile depth occurs at 4 a.m. So look at this. Not only do we have the minimum depth and the maximum depth, but we also know when those things occur. Now, there's something else we know here. We know the period. And the reason it's important for us to know the period is because that's going to help us define the B component in our model. Now, if we go, let's think of how long it takes to go from high to low, back to high. Okay? How long does it take to go through a cycle? At 2 a.m., we're at low. Then at 4 a.m., we're at high. So that's 2 hours. That's half a period. It's got to get back down to low. So it looks like our period is 4 hours. Okay? Now, here's why that's important, because we have this relationship. Remember, we think of sometimes when we're calculating the period, we take 2 pi divided by b. If we're given b, we can calculate the period by just dividing by b. But we could also use a little algebra and say b is equal to 2 pi divided by the period. So here's what we've got. B is equal to 2 pi divided by 4, which is pi over 2. So we've got the B component of our model. Yeah. So let's see what we've got here now. Let's go back and find the average depth of the methane. Well, that's going to be the vertical shift. It's going to be 2 plus 10 divided by 2, which is 6. Okay? Then we ask, well, how high does the water get from that? It goes up a certain amount and it goes down a certain amount. That's the amplitude. So A is equal to 4. It goes up 4 and it goes down 4. Now, when does it have a maximum depth? Well, it's going to have a maximum depth at 4 a.m. So here's what we've got now. We've got y equals 4 cosine pi over 2 t minus 4 plus 6. And there's our model for the depth of the methane over time. Okay, now this problem right here is kind of an example of how using radians can be helpful to us. So you like to ride your penny farthing, let's say, and the front tire has a radius of 2 kilometers. My goodness, 2 kilometers. What's going on? Okay, so let's just do that. 2 kilometers. Okay. When you ride, the front tire makes 3 revolutions per minute. Okay. So we're just dealing with the front tire, and it's 3 revolutions per minute. Okay. How long will it take you to go 100 kilometers? Okay, so that's the question. And this up here is kilometers. Okay, well, here's the essential information. And this problem is not difficult if you just realize, well, how far is it around that tire? Well, the distance around that tire is, so here's the circumference of the tire. It's 2, remember the circumference, 2 pi r, right? So this is 2 pi, and what was the front tire? Okay, the radius was 2. There's the distance around the tire, right? Do y'all see that? 2 pi r, that's a circumference. So this is 4 pi. Okay? Now, every time that tire makes a revolution, you go that many kilometers. Right? Y'all see that? Now, let's figure out how many kilometers per minute. What was it, per minute? Yeah, how many kilometers per minute is going to be 3 times 4 pi, which is 12 pi. This is how many kilometers you travel on your penny farthing every minute. Okay? Now the question is, how many of those are in 100 kilometers? Because every minute you go 12 pi kilometers. So if you're wanting to know, well, how long is it going to take to go 100 kilometers? You got to say, well, how many of those are in there? Because every minute you go that far. So it's 12 pi. And whatever that turns out to be, that's how long it will take you to go 100 kilometers on your penny farthing. As the giant that you are. Now, also remember this. On the test, you'll need to be able to convert between radians and degrees. Okay? So let's just hearken back to how we do that. If we go radians to degrees, okay, radians to degrees. So let's just look at an example. Let's suppose we have pi over 10 radians, and we want to convert that to degrees. We're going to multiply that by 180 over pi. This is how you go from radians to degrees. So I guess this would be 18. Okay. Now, if you want to go from degrees to radians, okay, so notice from radians to degrees, you multiply by 180 over pi. Let's suppose you have 20 degrees. Well, what you want to multiply by is pi over 180. Pi over 180. And that will give you the radians. So what is that going to be? 180. So this is 18. What is this? And this is 2. So pi over 9. that right? Pi over 9 radians. Okay. Now, also, remember, we've got degrees, minutes, and seconds, and decimals. So, let's look at degrees, minutes, and seconds, and we want to convert that to decimals. Okay? So, let's suppose that we have 8 degrees, 10 minutes, and 4 seconds. Whoops, what am I doing? Look at that notation. Okay, there we go. We want to convert that to decimals. What we're going to do is just calculate this. 8 plus 10 over 60, these are all degrees, plus 4 over 60 squared. Just run that through your calculator, and that will be your decimal. Okay? Because, yeah, this is 10/60ths of a degree right there. This is 4 3,600th of a degree. Okay. Now, let's suppose we want to go from decimals to degrees, minutes, and seconds. So let's suppose that we've got 8.23 degrees. Now, what you're thinking of here is you've got 8 full degrees and a fraction of another. So this is 8 full degrees, and then you want to know, well, how many minutes? So you take the 0.23 and you multiply by 60. This is how many minutes you're going to have. And you get 13.8. Okay? So this is 13.8 minutes. Well, there's a fraction, so there's 13 whole minutes. We want to find out, well, how many seconds is that? In other words, we want to say, okay, it's 0.8 of 60. So I'm going to take 0.8, we multiply by 60 again, and we get 48. So now we're done. We've got 8 degrees, 13 whole minutes, and then 48 seconds. And there you have it. You've converted. So we need to be able to do those types of conversions. Okay, now, as far as graphing goes, we focused on sine and cosine. But we also have the others, right? We have tangent, cotangent, secant, and cosecant. Now, remember this. Tangent, and we're just going to do rough sketches here, but remember, tangent and secant, they're kind of alike, and they have asymptotes at pi over 2, at the pi's over 2. Cosecant and cotangent have asymptotes at pi. So I want to look at this first one right here, this tangent. So I have this. I have 1 pi over 2. Remember, I go 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, and so forth. And remember, at the pi's over 2, I should have written these. Okay, so remember, at the pi's over 2, we have the asymptotes, right? So, okay. And this is 2 pi here. And didn't get these exactly straight, but I'm glad y'all are merciful. There we go. So if we want to get a sketch, the graph, and over here we have negative pi over 2, of course, but the graph is going to go, it's going to go like this, and like this. This is 2 pi here. Okay. In other words, we get the basic sketch. So look, you have asymptotes at pi over 2 and zeros at pi. That's for tangent. But this is not tangent. This is tangent for x. So what we have to do is we have to come back and divide all these by 4. So this is pi over 8. This is pi over 4. This is 3 pi over 8. This is pi over 2 for that, right? Do y'all see that? Okay. So you just remember, we're just doing rough sketches. I mean, look at that ugly graph. We just want to know basically where things happen here. Where are the asymptotes? And we think, okay, normally tangent has an asymptotes at pi over 2. Well, now we divide all those by 4. So let's look down here at this one, at secant 6. Okay, so here we go. We got 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay, we got those. And of course over here is 0 pi over 2, which is just, 0. And then what I want to do, I want to put the asymptotes here. Okay. There would be an asymptote over here, asymptote over here. And remember, the thing about secant is it's never going to touch the x-axis, unless it's been shifted down or something. But we're not dealing with that right now. So it's just going to be these parabolic-looking things, alternating, some opening down, some opening up, and they alternate. So look here. So we want to know where to start. Well, at pi, remember secant is 1 over cosine. Now cosine is -1 at pi. So we start down here like this. And then we alternate. Okay? And it just goes on forever like that. But we got to divide by the 6. So this would be 12. This would be 6, 12. And this would be pi over 3. The important thing is to remember that the asymptotes for tangent and secant occur at pi over 2's. And then you've got these transformations to worry with. But just get the basic shape first, and then go through and divide by 6. Okay. Now for cotangent and cosecant, they have asymptotes at the pi's. Okay, so here we go. Here's 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. Okay. Whoops, wrong one. Okay. So now we have asymptotes here, here, and here at the pi's. Oops. I tried to scoot it over. I can't. Okay? Now remember, okay, tangent's always increasing, cotangent's always decreasing. So, cotangent goes like this. And we divide by 2 at the end. Tangent's always increasing, cotangent's always decreasing. Just some fun trivia to remember. Now, Cosecant, same thing. 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. I make the asymptotes. Whoops. What am I doing? I got out of control there. The asymptotes. They're at the pi's, aren't they? Okay, now, remember, cosecant is also a bunch of these alternating parabolic-looking things, right? So we want to know, okay, this one at pi over 2, is it opening up or down? Well, this is 1, cosecant is 1 over sine, and sine of pi over 2 is positive. So that tells us, okay, it's opening up. Like, ooh, maybe not yellow. Maybe nice pink here. It's going like that, and then we alternate. Yeah, and then this one over here be down. There it goes, alternating like that. But remember, tangent's always increasing, asymptotes at pi over 2. Cotangent's always decreasing, asymptotes at pi's. So we didn't get really much into those. We're just, you just need to know the basics about them. What you see more often is sine and cosine.